Now let's start chapter 10, which discusses spontaneity and also introduces two more state functions called entropy and free energy. In this chapter, the main idea is we're trying to predict if a chemical reaction will occur under certain conditions. This could be really helpful to us as chemists because if we're studying a specific reaction and we're trying to go into a lab and do the reaction, you could spend years and years and years doing a reaction, or you could do a quick calculation before you even start to make the prediction as to whether or not the reaction is even possible. This can save you a lot of time. If you make the prediction that the reaction is just not going to occur under a specific set of lab conditions, then you don't have to waste years of time trying to make the reaction happen. Now, if you do a prediction and find that a chemical reaction does not occur under a certain set of conditions, we can think about what you can change in order to make the reaction happen. Additionally, this is going to have consequences and connections to the value of the equilibrium constant for a reaction. And this is going to allow us to get some explanation as to why some chemical reactions have large equilibrium constant values, why they're very product favored, and why some reactions have small equilibrium constant values, right? Why are they very reactant favored? And let's say that you're doing a chemical reaction that has a relatively small value of K, so you're not able to produce very many products. You can think about how you can change the reaction conditions in order to make the value of K bigger in order to generate more product. That has a lot of very important applications in the pharmaceutical industry because in the process of making pharmaceutical drugs, you'll often do a series of many reactions to make the drug that you're trying to synthesize. And a lot of these reactions are equilibrium reactions, and they have fairly small values of K. And so you're not able to produce a significant amount of your product over the series of reactions that you do. If you could figure out how you can drive the reaction more towards products and make the value of K bigger, then you might be able to make more of the product that you're trying to produce, and that allows you to have a more efficient operation of your plant, and it also helps you to save some money as well. So you're not wasting as much money on starting materials because it doesn't take as much starting material to make more product. Let's begin this chapter by talking about spontaneous processes and what a spontaneous process is. In thermodynamics, we define a spontaneous process as being one which proceeds on its own without continuous external influence. Now, spontaneity is not at all related to speed. So, for example, the conversion of diamonds into graphite is a spontaneous process. This is a process that will occur on its own without continuous external influence. But the reaction is incredibly slow. This reaction takes somewhere on the timescale of millions to billions of years to occur. And so this is how, diamond companies get away with saying things like a diamond is forever. That's actually not a factually correct statement. A diamond is not forever. If you have a diamond and you let it sit for a few million or billion years, it will turn into pencil lead. But the diamond company is assuming that you will not be alive for long enough to see this reaction occur, right? So spontaneity has nothing to do with speed. We're just interested in knowing, will the reaction ever happen, not how long does it take to happen. Let's talk about some examples of some spontaneous processes. A ball rolling down a hill would be an example of a spontaneous process. You may need to give the ball a push to get it started, but once the ball is rolling, it will continue on its own without continuous external influence. You don't have to be pushing the ball and pressing it all the way down the hill. Once you give it a nudge, it will go downhill on its own. Ice melting at room temperature is spontaneous. If you take an ice cube out of your freezer and you leave it to sit on your tabletop at room temperature for a few minutes or an hour, it'll melt on its own. Any chemical reaction that occurs without the need for a continuous external influence would be a spontaneous process. Mixing an acid and base together and having them neutralize one another is a spontaneous process. The combustion of methane is also a spontaneous process. And it's a nice example for us to look at here because this allows us to talk about a continuous external influence versus just giving a reaction a push. For the combustion of methane, you do have to give the reaction a spark in order to get it going. But once the reaction starts going, it proceeds on its own without the need to continuously intervene. So similar to ball rolling down a hill, you might have to give it a push to get it started, but once the ball is rolling, it'll roll on its own. The same thing holds true for, let's say, this combustion reaction. You have to give it a push, you have to give it a spark to get it going, but once it starts, it's able to proceed on its own without you continuously intervening. All right, let's take a look at another example of a spontaneous process. What we have here is some gas that's in a container that's partitioned off into two parts. And on one side, you have all the gas molecules, and on the other side, you have nothing. It's just a vacuum. You're going to remove the partition, and then let's think about what would happen to the gas after having removed the partition. As you might expect, after removing the partition, the gas should expand to fill the entire container. That's a spontaneous process. The gas will expand into the vacuum, and it'll fill whatever space you give it. But now let's think about the reverse of this process. Will all of the molecules in the container suddenly just move to one side of the container spontaneously? Or maybe more relevant to us, what would happen? Would it be possible for all of the oxygen molecules in the room that you're sitting in to move to one side of the room, and hopefully it's on the side that you're sitting on, and hopefully it's not on the other side of the room, right? Because otherwise you're going to run out of oxygen. So will all the molecules move to one side of the room spontaneously? We know that that's not going to happen. The molecules are going to remain evenly distributed. And thankfully, that is the case because, right, otherwise we'd have to worry every minute about whether or not we're suddenly going to not have oxygen in our room. The molecules will remain evenly distributed throughout the room. And in fact, what we can say is that the reverse of any spontaneous process is non-spontaneous. So the gas will expand to fill the entire container spontaneously. It will not just suddenly go back to being all on one side spontaneously. That's a non-spontaneous process. And in addition to that, you can consider the other examples that we've talked about of spontaneous processes. Said that it was spontaneous for a ball to roll downhill. It is not spontaneous for a ball to roll uphill. That's not going to happen on its own. For a ball to roll back uphill, you would have to push the ball up the hill. You would have to continuously intervene in order to make that process happen. And so that's not a spontaneous process. Said that the melting of ice at room temperature is a spontaneous process. It would be non-spontaneous for liquid water to freeze at room temperature. The reverse of any spontaneous process is non-spontaneous. Now, let's get a model for why this would be the case. We're going to consider a system that contains 4 distinguishable molecules. And we're just using the number 4 here because it's a lot easier than having to deal with, thousands of molecules. So just a small system with just 4 molecules. And we're going to put the molecules into a box and put all 4 of them on the left-hand side of the box. And we're going to count the number of ways that you can arrange the molecules. If you have 4 molecules and all 4 of them are on the left-hand side of the box, that's the only way that you can arrange the molecules. There's only one, what we would call microstate, or one arrangement possible in this situation. Let's now think about what would happen if we start distributing mass throughout the box. Now putting 3 molecules on the left and 1 on the right. And we can think about how many arrangements or how many microstates would be available to us in this case. So we don't have to just have molecule number 2 on the right-hand side. You could also put molecule 1, 3, or 4 on the right-hand side. And what that gives us are 4 different ways, or 4 different microstates, or 4 different arrangements that are possible when you have 3 molecules on the left and 1 on the right. We can further distribute the mass through the box and now look and see what happens if you have 2 molecules on each side. And you can draw out all the different combinations if you want, and what you'll find is that there are 6 different ways that you can do this. Just to kind of summarize, when we had all 4 molecules on the left-hand side, there was only one possible arrangement for that. When there are 3 on the left side, there are 4 possible arrangements. And when there are 2 on the left side and 2 on the right side, there are 6 possible arrangements. Let's think about which of these situations is the most likely to be observed. We would expect that it's more likely to observe the situation where you have 2 molecules on the left side and 2 on the right side because there are more ways that you can arrange the molecules that way. There are more possibilities. You have a better chance of observing that, right? You have 6 times the chance of having the molecules equally distributed versus having all 4 on the left-hand side of the container. Now, you may look at these numbers and say, well, it's only 6 times more likely that the molecules are evenly distributed, right? So Does that mean that it's only 6 times more likely that all the molecules in this room would be evenly distributed and there's a good chance that the molecules could all move to one side of the room? The truth is that that's not the case. And the reason for that is when we're dealing with our everyday lives, we're working with an ensemble of many, many, many more molecules than just four. This goes into some ideas of statistics here, right? And it deals with the law of large numbers. If you flip a coin twice, are you going to guaranteed get heads one time and tails one time? Not really, right? There's a good chance that you can get heads twice or you can get tails twice if you're just doing 2 trials. Just like how if you only have 4 molecules, there's a reasonably good chance that you could have a situation where all 4 molecules are on the left. There's still a better chance that it's 2 and 2, but you also do have a sizable chance of all of them being on the left side. Now, if you start dealing with a larger number of trials, if you were to flip a coin 1 million times, are you likely to see heads 1 million times? Not really, right? If you flip a coin 1 million times, it's going to tend to converge on what the expected value is for that problem. You're going to see most likely something very close to 500,000 heads and 500,000 tails, this equal distribution here. And similarly, as you increase the number of molecules that you have in the room, that is going to cause you to converge on the most likely case of having an equal distribution of the particles. If you're talking about our everyday lives, if the molecules that are in this room, you're talking about quantities that are in the mole range. And so if you're talking about Avogadro's number of gas molecules, the chances of all of the molecules moving to one side of the room becomes infinitesimally small. The chances of them all moving to one side of the room would be somewhere on the order of 1 over Avogadro's number factorial. This is an incredibly small chance. And you can do the math on that. I did a few years ago and found it would be the same as the chances of somebody hitting the Powerball lottery every single day in a row for 1 billion years straight, right? Like that would be amazing if it could happen, but like it's not going to happen, right? So this gives us some idea of why it would be that you don't have to worry that all the molecules will move to one side of a room. Probability and statistics say that the chances of that happening are vanishingly small. Now, let's talk about how that relates to thermodynamics. There is another state function that we're going to introduce here called entropy. We'll use the letter capital S to represent that. And this is going to be the driving force for spontaneous processes. Ludwig Boltzmann came up with an equation that says that entropy is equal to K sub B, which is a constant. It carries a value of 1.38 times 10 to the minus 23 joules per Kelvin, times the natural log of omega, where omega represents the number of ways that you can arrange the particles. And that's where the idea of probability and statistics starts relating to entropy. The more ways that you can arrange the particles, the higher the chances are of you observing that situation. And the higher the chance of you observing that situation, the higher the entropy of your system, right? Because when you look at the equation, if you increase the value of omega, that also increases the value of S. So the more ways that you can arrange the molecules, the more likely you are to observe that, and the higher the entropy of the system. Nature tends towards situations of higher entropy. Boltzmann came up with this equation, and at the time that he came up with the equation, people really criticized him a lot and said, like, I don't understand this. I don't understand why this is important. No one really believed that there was any relevance to it. But over time, as people developed thermodynamics further and as people discovered quantum mechanics, things changed, and it ended up that people came along and realized that what Boltzmann was talking about made sense and it was right. And so he prevailed in the end. Unfortunately, he didn't get to live to see that, but he prevailed. And so much so, and the work that he did was so important that his equation, S equals K times the log of omega, ended up being engraved as the epitaph on his tombstone. So I think it just goes to show, like, disregard what the haters tell you. With that, that brings us to the end of this first section. Next, we're going to talk about the isothermal expansion of an ideal gas and talk about reversible processes and how that relates to entropy.